Welcome to this explainer. Today, we're literally putting on our hard hats and grabbing our clipboards because we are initiating a massive manufacturing audit. We're looking at the ultimate industrial case study, how mass production, supply chain management, and sheer raw engineering throughput actually decided the fate of the Second World War. As a manufacturing engineer myself, I've always felt like history books spend way too much time obsessing over the generals and nowhere near enough time on the factory floors. So we're going to fix that right now.
To kick off this audit, let's establish our baseline thesis with a pretty blunt quote. Wars are about competition in production. The side that can produce more is always going to triumph. I mean, that perfectly captures the reality of modern conflict, doesn't it? This wasn't just a war of battlefield tactics. No, this was a war of assembling lines, material sourcing, and breaking massive production bottlenecks. If your factory floor can outscale the enemy's factory floor, your victory basically becomes a mathematical certainty.
And to really prove that point, just take a look at our first staggering KPI. Scaling from a baseline of just 790 ships before the war, the U.S. Navy hit 6,768 active vessels by VJ Day. I mean, wow. That number shows exactly the kind of unprecedented throughput we're auditing today. How in the world do you scale an operation by nearly 1,000% in just a few short years? Well, let's dive in and find out.
Section 1. Standardizing the skies, from craftsmanship to continuous flow. Let's start our audit over in the aviation sector, where the Allies were facing massive production bottlenecks early on, and they urgently had to figure out how to transition from craftsmanship to continuous flow. Now, what's fascinating here is the stark contrast between two completely different manufacturing philosophies. On one hand, you've got the bespoke British approach. They were building the absolutely incredible Rolls-Royce Merlin engine using highly trained specialists, basically handcrafting each engine. It was beautiful, but they just couldn't scale it. On the other hand, you have the mass production optimization spearheaded by the American company Packard. Packard took those British blueprints, adopted the measurements, and created specific machine tools that allowed totally unskilled labor to churn out identical, standardized parts at 3 times the speed. A real game changer.
But hey, mass production wasn't just some instant magic bullet. Take Ford, for example. They built the massive Willow Run factory specifically to manufacture the B-24 bomber. It was supposed to be a total marvel of engineering, but early on, it earned the incredibly embarrassing nickname, Will It Run? It was a complete disaster at first. So what was the core bottleneck tripping them up?
Well, it comes down to a really harsh engineering truth. You cannot mass produce a prototype. The military just kept changing the blueprints on them. And as any manufacturing engineer will tell you, constant design changes and mid-production revisions will completely wreck the flow of your assembly line. Ford finally had to put their foot down and demand that the military freeze the design. And you know what? The minute they did that, the line unblocked and Willow Run actually hit a peak throughput of 650 bombers a month. And this logic scales up into even more complex engineering. Boeing took throughput even further with the B-29 Superfortress by implementing a system called multi-lining. Listen to this. A single B-29 had over 1 million rivets. To handle that absolute nightmare of a build, they ran 6 assembly lines in tandem, merged them down into 3, and synchronized 1,400 different suppliers so that one single delayed shipment wouldn't stall the final assembly. It was an absolute masterpiece of workflow orchestration. And the resulting key performance indicators really illustrate this massive shift. Back in 1939, the US was vastly outproduced by both Germany and Japan. But by freezing those designs, standardizing the parts, and utilizing techniques like multi-lining, the US didn't just catch up. By 1945, they were outproducing the Axis by a factor of 6. That is a total manufacturing turnaround.
All right, moving right along. Section 2. Modular Maritime Assembly. Hacking the shipyard. Let's leave the skies behind and move our audit down to the naval yards. We're going to look at how an industrialist named Henry J. Kaiser applied Detroit's automotive manufacturing principles to literally hack the traditional shipyard.
So before Kaiser came along, ships were built one at a time, from the keel up, and they largely used rivets. It was incredibly slow. To fix this, Kaiser introduced what's called sectional construction. He transitioned his workforce away from riveting and over to welding, which was way faster to train, by the way, and he divided the ship into distinct modules. This meant 95% of a Liberty ship could actually be pre-assembled in completely different areas of the yard before it ever even hit the slipway for final joining.
Seeing this throughput in action is just mind-blowing. At the start of 1942, it took 210 days to build a single ship. But by relentlessly optimizing that line and leaning into modular construction, they slashed it to 156 days, then down to 106 days. And at their absolute peak, they managed a record-breaking assembly time of just 4 days. 4 days. That is efficiency at its absolute finest. And honestly, the production results speak for themselves. In 1942 alone, the U.S. pumped out 1,800 major naval vessels, compared to Germany's 244 and Japan's 68. This massive surge in modular production completely overwhelms the German U-boat threat, because suddenly the strategy wasn't just to hunt submarines, it was to mathematically replace cargo ships faster than the enemy could possibly sink them. Okay, Section 3. Decentralizing the supply chain, scaling the Manhattan Project. Our audit is now pivoting to perhaps the most complex operation of the entire 20th century. We are tackling the ultimate supply chain nightmare, industrializing theoretical physics. This is the massive engineering paradox that General Leslie Groves faced when he took over the Manhattan Project. I mean, think about it. How do you build an industrial-scale factory for a highly volatile product that has only ever existed in the minds of theoretical scientists? He had zero blueprints, no established safety protocols, and a terrifyingly tight deadline. Well, the solution Groves went with was extreme decentralization. He deliberately separated these highly dangerous and secretive production nodes across the entire globe. They sourced raw uranium from the Congo, refined it in the deeply isolated valleys of Oak Ridge, designed the actual weapon down in New Mexico, and built massive nuclear reactors out in Washington state. It was basically a macro assembly line employing nearly 100,000 people, most of whom had absolutely no clue what the final product actually was. And this project perfectly highlights exactly why extreme quality assurance and safety engineering matters so much. When the chemical company DuPont built the Hanford reactors, some scientists actually complained they were being way too cautious. But DuPont insisted on built-in redundancy, so they installed extra reactor tubes. Thank goodness they did. When the reactor was first fired up, it inexplicably shut down due to a totally unforeseen chemical byproduct called xenon poisoning. Because DuPont had over-engineered the system, they had the surplus capacity to push past the poisoning and restart the reaction. Basically, good engineering saved the entire project. Section 4. Designing for extreme reliability. Small arms and the environment. For our final area of focus, let's bring this audit all the way down to a micro level and assess small arms engineering. Because here, we see two brilliant but completely opposing philosophies when it comes to achieving ultimate reliability. First up, let's look at the American approach pioneered by Samuel Colt. Colt basically invented the modern assembly line for weapons. He standardized machinery, divided up the factory floor by specific tasks, and most importantly, he utilized fully interchangeable parts. This meant that a broken weapon could theoretically be fixed anywhere in the world just by grabbing a standard identical component out of a bin. It was an absolute triumph of precision engineering. But then, on the flip side, we have the Soviet approach with the AK-47. Embodied perfectly by this quote, loose clearances. Instead of precision, the AK-47 relied on cheap, stamped metal and intentional loose clearances between all the moving parts. The idea was, instead of trying to keep dirt out with super tight tolerances, just assume dirt is going to get in anyway. They left enough room inside the gun so it would literally just grind right through the mud and keep functioning. It was effectively idiot-proof and weatherproof. The big takeaway for us here is a golden rule of engineering. You must design specifically for your user's environment. Colt achieved reliability through high precision and a robust supply chain of identical parts. Kalashnikov, on the other hand, achieved his reliability through deliberate looseness and rugged simplicity for a soldier isolated out in the mud. Both solutions are genuinely brilliant, and it proves there are multiple, valid ways to optimize a machine's lifecycle. Section 5. The final postmortem. Throughput won the war. All right, to wrap up our manufacturing audit today, we have to look at the final postmortem. And honestly, the data we've reviewed proves beyond a shadow of a doubt that it was modularity, frozen designs, extreme QA, and massive decentralized supply chains that ultimately turned the tide of the 20th century. Throughput literally won the war. So I want to leave you all with this final, somewhat provocative thought. During the war, survival absolutely depended on raw, redundant, factory scale and having that massive surplus capacity. But today, our global manufacturing relies on hyper-optimized, just-in-time supply chains with virtually zero redundancy. So if a massive global crisis hit today, would our incredibly lean systems actually hold up, or would they just break? It's a pretty serious engineering vulnerability, and definitely something for us to chew on until our next audit. Thanks so much for joining me on this explainer. See you next time.